Okay, then uh, previously we finished with this topic biconditionals, and now uh, this is example 11, not related to biconditionals but related to truth table. How we can construct a truth table? We already is practicing this. How we can construct a truth table? But, but now this is the proper question related to truth table. And the question is construct the truth table of the compound proposition, and compound proposition is given. So when some equation or compound proposition will be given to you and you have to construct the truth table, what is the first thing that you have to do? Count the number of variables. And there are only two variables here, so that would be P and Q. You can say that would be your input columns. And you can evaluate the possible combination of the values for them by using your own mind, using the methods that we have already studied. There are two methods, one with the formula, other is just hit and try. And then, so here, and then here, so then you have to calculate this left hand side. But for this left hand side, we have the P, but we don't have the negation Q. So that's why we will calculate negation Q first. And then after calculating it, now we have this column negation Q and the P available in the truth table. So we can now calculate the disjunction. So that's why in the next column, we are calculating disjunction, which is inclusive OR. And then we will calculate this right hand side, which is simply the P and Q and the conjunction between them. So that's why we will now evaluate the conjunction and their possible values from these input values. And after that, only one thing is remaining, which is implication. So now, but we have these two columns already in the truth table. So now apply the concept of implication. So this is the now final form of this compound proposition, and we will apply this implication. By considering these two column values, we can, and after having the definition of implication, you can calculate these values. So I'm not explaining because you already know. So now the next is precedence of logical operators. In programming languages, normally if you have uh, arithmetic operator like plus, minus, multiplication, division, or even power, then these operators normally have some precedence, which means that which operator, if they are appearing in a equation, plus, minus, multiplication, division, then which operator will execute first? Plus or multiplication, division or minus. So this is called precedence. So, and here we have studied the connectors already, which is starting from negation, then conjunction, inclusive or exclusive or, and then implication and by implication. These are operators, these are connectives. So then if they all will appear in a equation, then which operator will execute first? This is the question. So this is, and here it is the table. If you have all these operators in an equation, then negation will have the highest priority. It will be executed first. And after that, conjunction. And after that, disjunction. And after that, implication. And after that, double implication. But this is the precedence. But in an equation, you can control if you want to execute even the less prioritized portion. If you want to execute it first, then you can put parentheses over there. You can control the execution of different parts in an equation by using the parentheses. What is parentheses? The small brackets that you have. Okay, these are called parentheses. So, for example, if you have some equation like that, here you have a parenthesis. So then what? You can say this is one part which will execute first because parentheses there, and this is another part which will execute first because the parentheses are there. The parentheses are there. So now, if you will execute it first, parentheses, if parentheses are there more than once in an equation, then you can go on left to right. So then it will execute first. And here P or Q, so you will calculate disjunction between these two parentheses, and then you will have some answer. Then you will have what? Some answer here. And then after that, this part, because parentheses are there, this part will execute. This is okay, one, and then this will execute at number two, and then you have the result of this one, and then this one will be executed at number three. If you, for example, if you don't have, if you don't have P or Q and what? And negation, if you don't have parentheses, then what will happen? Negation, yes. This is what now table will help you. Negation will execute first, and then conjunction according to the table. Number two is conjunction, so the result of this one and that one will execute. And then you will have some result here. This one and that one will execute. So if you don't have parentheses, then you can see in this on this whiteboard that how it will evaluate. If you don't have parentheses here, then what will happen? Only for recording, I am just repeating. If we don't have parentheses here, then negation will execute first. And then this conjunction will execute. And then the result of this disjunction will be executed. Similarly, here, if you have something like that, negation P R Q, and if you don't have any parentheses, then this negation P will execute first. Whatever the result, that would be conjuncted with this Q. Then conjunction will be executed. And here, P and Q and R, you don't have any parentheses here. Then what will happen? P conjunction Q will execute first, whatever the result is, and then disjunction. And then the result of this and this R and disjunction will be applied afterwards. And if you have this thing, what will happen? You can see disjunction is the third priority and implication is the fourth. So disjunction will execute first. And then whatever the result, that would be implied with this R. So basically, if there is no brackets there, then by considering these different operators, you can understand that this has the highest priority. So it means implicitly, by default, the parentheses are there. By default, it is not seen, but by default, this part will be executed. This part will be executed. Just like if you will put parentheses, then that part will execute first. Anyhow, so this is the precedence. You only need this table. You only need this table, that if you don't have any parentheses in equation, then what is the order of execution of different operators? Now the things, this topic is easy. Logic and bit operations. Logic operations are bit operations. So what is bit? You already studied in computing fundamental what is bit. So bit is some unit which can take 0 or 1 value. It is, you can say it is just one unit or one digit. But when you say digit, it doesn't mean that 0, 1, 2, 3, 4, up to 9. No. It means 0 and 1 only. It means 0 and 1 only. Normally, binary bit we normally use for binary system. So binary system. Anyhow, so bit is what? It is some symbol which can take two values, can be 0 and 1. This 0 is equal to false and this 1 is equal to true. You know that. This idea was given by this man, John Tukey. Anyhow, leave it. A variable is called, leave it. Why? Because as they left the Muslim scholars, which they did, which they did too many things in the history, but they don't mention their names, and they mention their own name. So that's why. But honestly, I have still just mentioned. Otherwise, we are more honest than those people. I don't want to discuss, but anyhow, this is the fact. This is the fact. Uh, they have taken all the things who are mostly originated are founded by the Muslim people, and they have given their own names. But in there are some countries in Europe which are honest than as compared to others. For example, Germany. If you have some Muslim name there in the first, they will mention that name. But mostly countries are not that honest. Anyhow, uh, so we can we so there would be something if we have a Boolean variable. There would be some variable that we can call Boolean variable. And for example, in programming languages, Boolean is a data type, like integer, like float. These are the data types. Boolean is also a data type. And you can write Boolean as a data type, and then you can introduce some name for the variable, and that variable can take only values what? 0 and 1, true or false. So similar. So if you have we have a variable for some time for representing these values 0 and 1, then we will call that variable a Boolean variable. And what values it will take? Only these two, nothing else. 0 and 1, true or false. Anyhow, what are the bit operations? There are some bit operations, which is and, or, exclusive or you can say conjunction, disjunction, exclusive or. And here, okay, if you have two Boolean variables x and y, if you have two Boolean variables like p and q, then what are the possible values? These are, you can say you can write true or false, or you can write 0 and 1. But here it is written into the form of 0 and 1 because now we are considering bits. And bit can take 0 and 1 value in machines, in computers. So anyhow, so these are the possible values: false, 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 true, true, false, true, true. Or now, but here in bits, we are writing it 0 and 1. So this is the same thing that you already have seen in previous slides. And then here we are finding what? Disjunction. Disjunction, this one. So that has the same definition. When any one value is true, you have the true. So that's why, for example, here, this is 1, so that's why true. This is 1, true. This is 1, true. Any one value, we need at least one value true, and then you have the resultant value true. Similar is the for conjunction, and similar is the exclusive or. When you have same values, it is false, and for opposite, it is true. This is the definition of exclusive or. This is with the same concept that you have studied in these previous slides. But we are only representing it with 0 and 1, nothing else. Okay. Now we have a new definition. So what is bit string? Bit string would be a new name. This is already you studied in computing fundamental. So what is bit string? If you have some sequence of zeros and ones, if you, for example, if I will write 0, 1, 0, 1, whatever coming into my mind, I am just writing, okay? This is not fixed that how I am writing 0 and how I'm writing. This is not. So this is what? This is sequence of 0 and 1. And this is called bit string. This is called what? Bit string, a string of bits. And then the length, what is the length of this bit string? You have to count these bits. And it is 6. So the length of this bit string is 6. So here, so that is definition. Now the example, the string is given. What is the length of this? You have to count 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is the length. 9 is the length. Now we have another example. Find the bitwise or, bitwise and bitwise XOR of the bit string this and this. Two strings are given to you. And you have to find what? You have to find OR and XOR. Why are we saying bitwise OR? Because we are dealing with the bits. So you have to find OR with the bits. You have to find AND with the bits. So that's what bitwise. Bitwise is not a different thing. Bitwise means we are dealing with 0 and 1, nothing else. So here we have two strings. The first, this one is written here, this one is written here, and now we have to find OR. You know the definition. OR is what? When only one value is 1, you will have the 1. So here one value is 1, so we are writing 1. One value is 1, so we are writing 1. We need at least 1. Here we have 2, so 1. Here 1. 1, 1, 1. 1, 0, we have 1. 1. Here we don't have 0, 0. Here we don't have, so that's why it is 0. Similarly, AND. What is AND? If any one value is false, result is false. So you can calculate these values with that definition. And XOR, when opposite, then it is 1. When has the same, then you have the 0. Hmm? So it's easy. It's easy. I will not give you these questions in the paper, okay? I will give you the hard ones. Okay. But when I will see that you are struggling, you don't have too much marks already, then I will give you this question. Okay. Anyhow, applications. Now the applications of propositional logic. So where we can apply this propositional logic. And now we will see, this is the first one. We can translate something into English and opposite. And then we will see how we can create system specifications. And then we will move on to Boolean search. This is the third use of propositional logic. And then we can solve logic puzzle. This is the fourth use. And similarly, we can build circuits, etc., etc. We will move on like that. So applications of propositional logic. So this is just a statement which is saying that either this is mathematics or sciences or natural languages, the languages that we normally speak. The statements in all these fields, sometimes the statements or sentences are ambiguous. They are not clear. They are not, sometimes they are not giving us the true meaning. What the sentence want to say, we don't understand. So this is what this thing is saying. So in this situation, so when the things are not clear, we want to use these propositional logic concepts to make them precise, to make them more correct. And one application is this: translate into English and vice versa. Vice versa means opposite, in reverse direction. So we want to make these statements or whatever more correct, more precise. Precise is the opposite of imprecise. Precise normally means correct. Imprecise means not correct. But precise means correct with details. And concise means correct with shortness. Short answer. Short answer. Precise means correct answer but with detail. Anyhow, leave it. That is another thing. So we want to make them precise and unambiguous. Ambiguous mean it is vague, it is not clear. So we want unambiguous, it is clear. So we want to make these statements useful and we want to make them precise and unambiguous. So the one way is to translate them into logical expressions. Logical expressions mean mathematical equations of propositions, okay? Logical expressions. Why we normally convert them into logical expression? Because if we have something as a logical expression, then we can analyze their truth values. If I will give you equation, you can build its truth table. And if you can build its truth table, you can see its truth values, what is happening with them at different situations. So this is what I'm saying. We can analyze truth values. We can analyze truth values, and then we can do some other things with that, and then we can finally conclude something from those truth values. So now this is just the first application we are going to see, that this is the first application where we are going to apply this concept of propositional logic. Let's see. We have an example. How can this English sentence, which is given here, how can this English sentence be translated into a logical expression? How can we convert this English sentence into a logical expression, into a mathematical equation, you can say? That mathematical equation will contain propositions with connectives or whatever. So now, first we have to read it. What is that? You can access the internet from campus. This is one sentence, and that is proposition. You can represent that sentence with P only if is a pattern in implication. In implication, if you will go back, so that's why I was saying only if. This is one pattern in implication. P only if Q. So P first, Q after. And now, so we have to convert these sentences into a logical expression, nothing else, into a equation. What is the meaning of this logical expression? Meaning equation of propositions. So you can access the internet from campus. Okay, I am calling this sentence P. Only if, okay, that is that pattern. Only if you are a computer science major, this is another sentence, I can call it Q. And then we have this connector or, and you are not a freshman. So I can call it maybe R. So I am calling this not. Not is negation, okay? Not is negation. And I am calling it R. So now I have to convert it into equation. So if I will write P and only if is implication, and then this sentence Q, and then this R, and not, okay, now it's up to me. If I am representing this sentence with not as R, I can write R. Or I can say I am taking R as what? You are a freshman. I'm taking this as a R, and then you have to represent negation here. And then you can put parentheses here that these are together because only if, and then you have two sentences. Just to make things more clear. Just to make things more clear. If you will not mention these parentheses, no issue. No issue. Okay. So this would be the equation then. This would be the answer then. And here I am representing A. You can access the internet from campus. I am representing it with A, not P. So just changing. And it is not necessary. You can take P and Q. But here, A. And then you are a computer science major. I am representing it with B. And you are a freshman. So I'm not taking negation. And I am calling it C. And only if is what? Only if P, only if Q. That is that pattern of implication. So finally, the equation would become what? A implies this is B or due to this or, it is or, and negation C. Understood? Any letters, yes, but small letters, because capital is fixed for some other thing, which is predicate in discrete mathematics. Understood? Anybody who have not understood? Yes. Why double R? Where double R? This one? For negation. Between negation. Where is double R? Oh, this is negation. So this is OR for disjunction, and you are not a freshman. I am calling, now it's up to me. Either I can take this not, this negative sentence as or I can convert it into positive first. You are a freshman, and then I can take it as R. And if I am taking positive sentence, then here I have to represent negation. And if I am assuming negative as R, then I don't have to represent this negation R. Okay. I don't, if I am taking this, you are not a freshman as R, then I don't have to represent this negation here because I am considering negative sentence as R. And then positive would be what? Negation R. So anyhow, now second application, system specification. Second application, system specification. Now, being a software engineer, you can collect the requirements for the software in a company. And if those requirements are more than 10 pages, and you have to find that these requirements that you have collected are consistent or not, you will understand what means consistent. Here I have explained. Are consistent means something agreeing with each other. So if you have to find that your requirements are consistent or not, and how you can do that? You can do that by analyzing those requirements sentences. And if you will see only sentences in theoretical form, then it would be very much difficult for you to analyze those 10 pages written with paragraphs, etc., that they are consistent or not. Then what is the way? The way is to convert those sentences into equations. And then those equations, you can see that what would be their truth values. What would be their truth values? When I say truth values, it means true and false both. So what would be their truth values? And if the assignment of truth values for all the sentences are true, if assignment of truth values that make all the sentences true, you will assign some truth values to the equations or to the proposition variables in those equations that you will form through from the sentences. So you have 10 pages of sentences, which is your requirement. First, you will convert those sentences into what? Logical expressions, or formulas, or equations. I am using different words for your understanding. Otherwise, logical expression is the best word. But I don't know, when I say logical expression, some students will understand, some will not. So that's why I'm using formula sometimes equation, or like that. So when you have these equations, when you have converted those sentences into the form of equations, now you can assign truth values to the propositional variables. So now, assignment of truth values to all expressions, to all equations, and if all equations are becoming true, then it means that the specifications or requirements are consistent. This is the definition. This is the definition now. This is the definition. Let's see the example. Determine whether these system specifications are consistent or not, and these are the sentences. Being a software engineer, you have collected these. I'm not giving you 10 pages, just 3 sentences. Okay. So determine whether these system specifications are consistent or not. And what is the definition of consistent? We will assign true or false values in the equations. And if all the equations are becoming true, then it means they are consistent. So you have to keep this definition in your mind. Otherwise, you can not be able to find the consistency between the equations.
Yeah, so in examining those true values, if you happen to find out that everything is false, it's also consistent.
No, the definition is true. Yeah, to make all specifications true. Here, what in the definition, what we are saying? We will assign the values.
Yeah, the reason I'm asking that question, because in the back conditional in the definition, saying if both P and Q have the same true value, so it will be false, it will be true. If they are all having the same value, then that's what will be true. Are we understand what in the back condition definition? Back condition.
Back.
Back conditional.
Okay, biconditional.
Yes. Say for the statement, for the statement to be true, both P and Q have to have the same true value.
This is biconditional.
Yes.
And here we have same value, so that's why it is true. But that is biconditional. This is the definition for the biconditional. Now I have given you the definition for the consistency, and you are mixing consistency with the biconditional. You are saying that if they are false, then it's true. So if all values are false, then we can say it is consistent. Behavior wise, attitude wise, it is consistent that all are becoming false. But consistency definition is different from the biconditionals. And the definition is saying that you will assign truth values. We will suppose, for example, we will assume that I'm taking P as a true and Q as a false. We will assign these values and then we will evaluate the equation. And if the equation will become true, if the equation will become true, and similarly all the equations are true, then it is consistent. So what values we are giving to them, this does not matter. Either you are giving false values, either you are giving true values, it doesn't matter. But if all equations are true, that is what means consistency. It will be okay, don't worry, it will be clear. Where is? So determine whether these system specifications are consistent, and system specifications are given here. The first sentence is the diagnostic message is stored in the buffer. You have to read it first, because only then you will have a complete picture in your mind. The diagnostic message is stored in the buffer. This is one sentence ending here, or this is connector. It is retransmitted. This is another sentence. And then diagnostic message is not stored in the buffer. This is the same sentence, but it is with negation. If the diagnostic message is stored in the buffer, this is again the same sentence, but using if and then pattern. P implies Q. If diagnostic message is stored in the buffer, then it is retransmitted. So there are, in all these three sentences, we have only two sentences. And they are different forms. Now what you have to do, you have to convert them into logical expression. If I will consider it P, then this or will become or. And this will, if I will consider the second sentence as Q, it is retransmitted. Then diagnostic message here not stored in the buffer. This will what? This will be what? Negation P. And here it will become what? If this is P and it is retransmitted is Q, it is retransmitted. Then it will, so this is P and this second one is Q, and it is what? If P comma then Q. This is what P implies. This is that form. So now you have that picture of all the equations. Let's see now. If my P is this message, if my Q is this message from the previous given information, then I can have these equations. First one is PRQ, second one is negation P, and the third one is P implies Q. Third one is P implies Q. So now I have these equations. I have to find that they are consistent or not. And what is the method? We have to assume truth values for these equations, And if all the equations on those truth values are true, then we can finally say that it is consistent. Otherwise, not. If any one equation has given us false value, we will say it is not consistent. So now, how we can start? So if I will start with equation 1, this one I have to assume maybe P, you can assume P is equal to true or Q is equal to false, or P is equal to false, Q is equal to true. It's up to you. You can assume any values for P and any value for Q. But what is the way? This one is easy because there is only one. I have to make this equation true. I am taking the short one because I don't have to assume too much things. So I'm taking the short one here, negation P. And to make this equation true, what I have to assume as a value for the P? So if I will take the value of this P false, this negation will make it true, and the equation, this equation, only this equation will be what? True. So that's why I'm taking this P as false. If we take P false, then negation P is true. Okay, one equation is true. Now go on with the other. So now your P is fixed. P is false for all.
Yes.
You cannot change this P. Okay, you cannot change this P until you are concluded or evaluated all the equations, or until you find some contradiction somewhere. So now my P is F. It is fixed now, and now I am going with this because both of these equations are same with two propositions. So I can take any. So now, so P is now fixed from the previous step, and now Q I don't know. So P is false. P is false. This is disjunction, and P is what? False. And I want to make this disjunction true. What would be the value I can take for Q? Because disjunction, if any one value is true, the equation will become true. So then what? For this Q, I will take what? I will take this Q as true. Because P is already a F, and it will not give me true value. So that's why I have to take what? Q as true. And then you will take P as F and Q as true. Then this equation will become what? True. Okay. Up to this point, two equations are true. Now we have the value of P and also the value of F. We have to put these values here, and we have to see that the third equation is true or not. If true, then consistent. If not, we have to go back. We have to assume maybe some other value for P. But let's see. Similarly, when P is F, the same, and Q is T, whatever it is from the previous step. Now put these values here. First one is false. First one is false. Second one is true. You will get true. Because according to the definition, first one is true, second one is false, then you will have false. But here things are different. So that's why it will become what? True. And now you have the three equations true. According to the definition, now you have assumed the value. So now you can say that when we will take P is equal to F and Q is equal to T, all equations will be true, and hence these specifications are consistent. Okay, this is the way normally software engineers find their requirements are consistent or not. So this is the second use that you have seen, that where you can use this propositional logic. Now Boolean searches, that is easy. In Google or in some other search engines, you are using this and, or, and not in the searches. In the searches, you normally use this and to connect two words together. For example, if you will write logical and like, and if you will introduce, and between them, if you will introduce and between them in the Google search, if you will use one word this, second word this, and you will use and between them capital, then it will search both words together in the databases or directories, and it will show you both words together. Similarly, you can use this or word. If you will use this or here, if you will use this word are between this logical and like, it will search those documents in which it will find logical or like are together because TT is true, FT is true, TF is true, according to the truth table. Similarly, you can apply this not symbol, not is negation. It will find what? It will find those, if you will use this not before any word, for example, if you will, so this can be used with one word. So if this is the word if you are searching this thing, not, and then the word excludes in the Google or whatever, what will happen? It will give you those documents in as a search result, which will not have this word. Okay, which will not have this word. So these things you are already using in Boolean searches. And if you are using and or not, this is called Boolean searches. So in the book, there is one or two theoretical paragraphs. You can read them by yourself. Okay, that is easy. So the concept is given to you where you are using these and or not, which is used in propositional logic.
Yes.
Now,
This book is
no, I cannot upload this book on the blackboard legally because I have downloaded illegally from the internet. Okay. So you can also find this book, just write the title, author, and edition. The PDF will come somewhere and then you can download it. Otherwise, I will share this book on the WhatsApp group. Okay, now logical puzzles. We can use this propositional logic to find different puzzles around us. This is also one of its use. For example, here, this is the question, and then we are going to solve it. This is the article actually by this Mulyan in 78 in which this puzzle is mentioned. So in that article, there is a puzzle about an island, and that island has two types of inhabitants there, two types of people living there. Okay. One type is called knights, and the knights always speak or tell the truth. Okay. And the other type of people are their opposites, and the name for them is knaves, and they always tell a lie. Okay. And then you are there and you encounter two people A and B. You are met with two people there in the island, and those two people are what? A and B. You met with these two people. And the question is, what are A and B? If A says, if when you met with A, then A says B is knight. And when you met with B, B says two of us are opposite to each other. Two of us are opposite to each other. So then the question is, what are these A and B? Okay. What are these A and B? So you cannot find the answer easily, okay, until you analyze it. So there is an island. On that island, there are two types of people living there, knights and knaves. Knights always speak truth, knaves always lie. You met with two people, A and B. A says, yes. Yes.
Yes, the one because it says the one and the two of us are the opposite times, so it's true.
The question is what? What are A and B?
A speaks the truth.
Okay, let's see. I'm not asking you to solve the puzzle in this way. I am asking to solve the puzzle by using propositional logic, by using truth values, and then that like that. Anyhow, and you will see what will happen. Your answers are right or wrong. You have given your answer, so you will see in the upcoming slides. So you met with people, two people A and B, and where A says that B is knight and B says that two of us are opposite to each other. And the question is what are A and B? So here we are assuming something first, and then we will analyze by using this propositional logic. We are assuming that A is night. We are making these statements. If A is night, we are calling it P. We are building propositions. We are creating propositions. And if B is night, we are calling this sentence Q. And then their negation P is what? A is knave. And negation of this Q is what? B is knave. This is what we are assuming. This is what we are making proposition from this information. Because what are A and B? What are the possibilities? A can be knight or knave, B can be knight or knave. These are the four possibilities, and you have to find something from these four. So that's why we are assuming those four first. We are making them as propositions. P is what? Knight, negation P is knave, about A. And Q is what? B is knight, and negation Q is what? B is knave, respectively. Now we will discuss them. And in the first case, we are supposing that P is true. We are assuming that this P is what? We are assuming that P is true, which is what? A is knight. We are assuming that A is knight. And whatever the information that you have, if A is knight, and this is K, by the way, okay? If A is knight always what? Speak truth. Knight always speak truth. And what A is saying? B is what? Knight. This is what it is saying. B is knight. So now go on with like that. And if B is knight always speak truth. And what B is saying? We are opposite. Here B is knight, and here we assumed what? A is knight. We started with A is knight. Again, look at this string, huh? So A is knight. This is what we are assuming. Knight always speak truth. So this is true. Speak truth. And what is the statement of this A? Here, B is knight. It means this is true. It means this is true because they always speak truth. So it means B is knight. So we approached here. We reached here at this point that B is knight. Here A is knight, starting with this one, and here we have reached B is knight. But we have not checked the statement of B yet. So what is the statement of B? If it is knight, it will speak truth. And the statement is we are opposite. So this is contradiction. This is contradiction with this supposition. Contradiction means you are saying something else and something opposite is happening at the conclusion. So it means that this is not true. It means that our supposition is not true. There is something wrong here. We are not getting our answer. This is what written here. This diagram that you have, I will explain it on the whiteboard if somebody will not understand, okay? So, but due to this recording, this is my restriction that I am here. Anyhow, so if P is true, P is what? A is knight. This is what we are assuming. A is knight. When P is true, which means this A is knight is true, then P is saying true because he is knight. I am using variables here according to propositional logic, which is saying the same story which I have explained here. So this A is knight, my P. So if it is true, P is saying true. And if it is saying true, what it is saying? He's saying B is knight. This one, B is knight. And that is what? Q. So it means Q is also true. It means Q is also true. And if Q is true, which is what? B is night. It means he's saying the truth. And Q is saying what? It is saying we both are opposite. P not equal to Q. Here, P is for the A, Q is for the B, and they are not equal to each other. This is what the statement of the Q. So this is what this disapprove the supposition of P. This last conclusion disapprove the statement of A, and A is saying B is night, and B is saying we are opposite. It means he is lying. They are not opposite. Contradiction. He is lying. So that's yeah. So we don't know if A is night. So then maybe P is equal to Q, but we don't know. But here we are on a contradiction. Here we are on a contradiction. So now we will change our assumption. Now we will change our assumption. Now we will think it is like that previously, like the consistent approach. First, we have chosen this value, but this value has bad effect. So now we will assume our assumption. We will change our assumption. So up to this point, our supposition with A is night is false, which means that A is not a night. Okay, then what? Now we are taking A is a knave. Or in variable form, we are taking P is equal to false. Here, P is equal to false. Negation P means this P is now false. And it is what? A is knave. So in short, we are taking A is knave now because the previous assumption is false. So now I am building it again. A is what? A is knave. Yeah. And knave speaks what? Yeah, tell always lie. And what is A saying? A is saying B is night. It means it is lying. B is not a night. B is knave. So I am here now at this conclusion. B is knave. But I have to check the statement of B. Half of the portion is done, but half is remaining. So B is knave. Up to this point, we have concluded that B is knave. So if B is knave, it is lying. Its statement is always lie. Knave. What is the property of knave? Knave always.
A is knave.
Yeah, let's do it again. So now we are assuming A is knave. And what is the property of knave? Always lie. So that's why I mentioned L, lying. So it means whatever the statement of A is, it is a lie. And what is the statement of A? B is night. So B is night. It means it is lying. B is not night. Then what it is? B is knave. So if B is knave, what is the property of B? Lying. And what is B saying? We are opposite. We are opposite. It means he is lying. They are not opposite. They are same. They are same. Yeah. It means they are what? Same. So A and B are same. And now we don't have any contradiction. In this analysis, we don't have any contradiction. This is the answer. Don't do hurry in answering these questions, okay? Don't do too much speed or quickness. Anyhow, so both are what? Here that is that discussion written in propositional variable form, which will give you hard time in understanding. So that's why these things are there. If you will see, whenever you will the QP negation Q negation Q, it is written. So whenever you will not understand, go what is P. So for example, P is false. So now we are assuming if P is equal to false, which means what? A is near. Here, if P is equal to if P, this is the P, and if it is false, this is that situation, huh?
Yes.
That is what it is written here. That is what it is written here. And then you will understand what P is equal to F means. But if you will read them directly, you will not understand anything. Until you compare what is P, what is Q, what is, then you will understand. Then you will understand. So if P is equal to what? False. It means negation P. Negation P is what? Is knave. And then knave, whatever the knave say, it is always false. So the saying of this P is false now. Because now our P is this. So it is false. And if A is, and what is the statement of A? A say B is knight. So it means it is false. B is not a knight. It is what? Knave. B is knave. And B is knave is what? It means Q negation, which means false of Q. So how we can represent? It means Q is false. Q is false means what? This Q is what? B is knight. And if it is false, what it will? The other option, knave. So that is this one. So it means which gives Q is equal to F, which is what? B is knave. This is now you reached at this point up to this discussion here. And then see, if B is knave, it is always lie. Saying of B would be false. And what B is saying? We are opposite. It means they are not opposite. They are same. This gives B is equal to Q. P is equal to Q. And here we don't have any contradiction. In this discussion, we don't have any contradiction, which is consistent. So that's why we are saying it is consistent with negation P and negation Q. It is consistent with when P is equal to F and Q is equal to F. And what is that situation in variable form? Negation P, negation Q. And hence both A and B are knaves. And there is, sorry? Yeah, here consistent means we don't have any contradiction. We don't have any error issue in our discussion. There is no anything opposing other thing. There is no anything contradicting other thing. And there is another example, which is muddy children example available in the book. Read it by yourself. It is example number 8 in this chapter. Now, that is easy topic. Logic circuit. We can build circuits by using this propositional logic. So this propositional logic, you can apply the concepts that you study here in this propositional logic for the design of what? Computer hardware. Computer hardware is what? It is computer circuits. And who gave this idea? Claude Shannon. So what is circuit? So there are two names that used for these logic circuits. Logic circuits are digital circuits. You can use any one of them. And these circuits will have some input, and in between the circuits that can process your input, and finally it will give you the output like a program. Like a program, it always takes some input, it will process, and it will give you the output. So the circuit is what? It will take some input into the form of signals. Those signals can be, for example, P1, P2, and so on, Pn. You can represent any variable. So, and then it will process, and then it will produce some output signals, and those signals can be S1, S2, Sn. And these signals would be into the form of bits, because now we are talking about hardware. And you know what is bit. So you know what is bit. So these input signals can be bits, 0 1s, can be 0 1s. In this P1, P2, and Pn, the value would be 0 or 1. And in these output signals, what would be the value? 0 or 1. So we can build these circuits by using some gates. There is another concept that is called gates. Those gates represent AND or something like that. That you already know what is AND: conjunction, disjunction, exclusive OR. So we now have a new name for those conjunction, disjunction, and exclusive OR in digital circuits. And what is that name? Gates. Let's have a look over there. So if there is a P and you want to make it negation P, then the thing that you can use is called inverter. Is called inverter. So this is basically the diagram for the inverter. This triangle in and then this small circle. So this is inverter. This is the shape of the inverter. And here this P signal is coming as an input, and inverter will make it opposite, and it will make it negation. It will give you the negation of the input. So P is coming and then you will get a negation. So this is the output and this is the input. And then the next gate, this is gate. These all three are called gates. This is called inverter gate, and this is called another gate, and the name of this is OR gate. And how it is, the diagram for this is a little bit curvy. A little bit curvy here. And this OR is taking, it can take at least two, 3, 4 are possible. So at least two variables it can take. P and Q are, these are the inputs. P and Q are coming, and then it will give you what? It will apply the, this is disjunction. It will apply the disjunction over it, and it will give you the bits like in that way. After applying the if you will get, for example, 0 and 1 here as a bit, what, this is the disjunction, what you will get here? 1, because this is what, if any value is 1, you will get 1. This is the role of this disjunction. But here we are taking propositional variables, so okay, go on with the variables. And now this is the AND operator. AND gate, not operator, gate, because we are discussing circuits. So now the term is different. Otherwise, it's the same concept. Otherwise, it's the same concept. So there are two, at least two, more is possible. So P and Q, and then the conjunction, it will give you this. This is the shape for the conjunction. It is not that curvy. Now, if this equation is given to you, you can build a combinational circuit, combinatorial circuit, or digital circuit, or simply circuit. If some equation will be given to you, you can build this. For example, if this equation is given to you, P and negation Q, what is that? So you have to look, this is conjunction, that is between P, and this is what? Inverter. So you have to introduce inverter, and then here it is also inverter, and then you have this disjunction. So you can start with P and Q and P and Q, and then you can use the inverter here. And then what you will get? You will get this minus Q or negation Q, and then P is coming here directly. So now after that, I can just change. You have these inputs, and then you have this conjunction. So now you can apply the conjunction operator, and then you can move on. So now this part is covered. This part is covered. And then you have this negation R. So, okay. Sorry, I am taking what? R without negation. And then inverter. And then it will give me what? Negation R. And then you have this part ready. And then you have this disjunction only left. So here you have the disjunction. You are giving this input here, giving the, and here. And whatever here, what you will write? This whole thing is now the output here. Okay, it's easy. It's easy. So that's how it is drawing, and it is displayed here. It is displayed here. Now we have an example. Build a digital circuit that produces the output, and this is now question P R negation R, then disjunction, and then negation P or Q or R, like that. This whole equation. And the given inputs are what? When you will see over them, you P, R, and Q. So these are, when given inputs are what? P, Q, and R. So now you cannot take negation R as an input. it is mentioned that P, Q, and R are inputs. So then you have to convert this. If negation R is there, so it means that you have to convert R into negation R by using the inverter. By using the inverter. So you can build this in the same way as we did here. In the same way. So what you will do? So this is one portion, P R negation R. If you will start with P and R, so okay, P is okay, but for negation R, you have to take R first, then inverter, and then you will have here you have P and then R inverter, and then you have negation R coming out of it, and then this P and R, and you have this what? Disjunction. So this is the disjunction, and you will get PR negation R. This part is now completed up to this point. And then conjunction, but here you have to solve it first. And for this, you have to solve this inner portion first. So that's why I can take Q and R, and by inverter, I will convert it into negation R. So that's why Q and R. So okay, this is Q, this is R. Through this inverter, I have this negation R. So Q and negation R, we have what? Disjunction. So now we have disjunction here, and we have this Q negation R. This portion is now covered. And now this portion and this negation P portion, now we are going to cover this one. And then this part will be ready for the next evaluation. So now here Q or negation R is here, and here I need this negation P. So that's why I'm using P through this inverter. It is negation P, and then we have, now we are going to solve it. Because on the one side I have this negation P ready, and on the other side this portion is ready, and between them is what? Disjunction. So now I applied this disjunction. So on one side this negation P is coming, other side is Q. So this is what I will get this one. So I will get, so now this part is solved here up to this point. And this portion up to this point is solved here at the upper side. And now these two are the inputs and I have to cover this and these two are the inputs, and that's why AND operator, which you can see, this would be now the final output, this whole equation. Okay. Okay, I am stopping here, and then this is the new section. We will start inshallah in the next lecture.